you to, what's the difference? It's 210, 203, 30%. Welcome everybody, welcome to the seminar. I'm very happy to present Aris Tritsis today for a very interesting talk having to do with magnetic fields, star formation, give you a little history of Aris. Aris got his PhD at the University of Crete, working on star formation with Tritsis and Russell.
Well, they were eventually they merged into one person.
Anyway, he did excellent work in his PhD, notably explaining, having an explanation of the existence of striations, density striations in molecular clouds, and also finding evidence for the existence of normal modes of oscillation in a Musca molecular cloud. So that's a very memorable thesis. And in fact, that went a long way to earning Aris the Merak Award, if I'm pronouncing it right, the very prestigious award from the European Astronomical Society for the best PhD thesis in Europe for that year. But I don't know. So that was a great start, and then Aris has been a postdoctoral fellow at Australian National University, and furthermore, he's actually a CITA alumni because he then came to Canada and he was a CITA National Fellow at Western University working with me. And that was a great time we had. But then he's gone on to a very good position as the only fellow at EPFL in Switzerland, where he is now. And so welcome back to Canada. Great to have you here. And without any more delay, I think we should get started.
All right, thank you so much. And before we begin with the presentation, I would like to say that it's an absolute pleasure to be back in Canada, especially because a lot of the work I'm going to present today actually started 3 years ago when I was a national fellow. So yeah, many thanks to Ms. Anton for inviting me and actually giving me the opportunity to come back and actually present my results. All right, so today I would like to talk to you about non-ideal dynamic effects and the mass-to-flux ratio in molecular clouds. Or very to be a bit more precise, I would like to talk about non-ideal negative effects during the early stages of star formation. So just so that we're all on the same picture in terms of scales and densities that we're going to talk about. What I'm showing over here is...
Can you hear us in the room? I'm sorry to interrupt.
Sorry?
We cannot hear you very well online. It's constantly breaking up.
Yeah, I need the speaker.
Is this any clearer?
Yes, this is much better. Yeah, thank you. That's great.
Okay, excellent.
Thank you.
All right. So, as I was saying, so just that we're all on the same page regarding scales and densities that we're going to talk about. Over here, I'm showing a region from Taurus molecular cloud, and you can see that there is this long filamentary structure that is formed over here that has a density of around 10 to the 4 particles per cubic centimeter. And inside this dense filamentary structure, we have these pre-stellar cores that have formed over here with a density of around 10 to the 5, 10 to the 6 particles per cubic centimeter or even more. And this is where eventually stars will form. Okay, so why is it important then to study this particular phase during the star formation process? Well, I think because there are observational evidence that at least to some extent the initial mass function is set during this stage of star formation. So what I'm showing here with these blue triangles is the mass function of pre-stellar cores. And as you can see, this core mass function resembles the initial mass function very well, indicating that there is a strong physical connection between the two. And then, of course, understanding the processes that lead to this core mass function and having a predictive theory of star formation is really important, not only for star formation, but also for planet formation studies, galaxy formation studies. Studying these molecular clouds is important for astrochemistry, and the list goes on and on. All right, then if star formation in this particular phase during the star formation is so important, then why haven't we solved it yet? And it turns out it's complicated. So the physical picture here is that we have two opposing teams. On the one team, we have the self-gravity of the cloud. This is, of course, counteracted by the thermal pressure. On larger scales, we have turbulent motions that can stir up the gas, and they can also provide a support against the self-gravity of the cloud. Once the first generation of stars within a present-day molecular cloud are formed, we have various feedback processes that will drive back turbulence and will also affect the cloud in various ways. And then finally, we also have the elephant in the room, which is the magnetic field, which can also support the cloud against its own self-gravity. It can affect the fragmentation properties of the cloud, and so on. But it seems that even upon considering all of these processes into our numerical simulations, we run into a problem, and we can't really reproduce observations. So what I'm showing here are 4 different simulations. Over here, gravity is only counteracted by thermal pressure. This is gravity versus turbulence. This is a simulation where the effect of the magnetic field is also taken into account. And then finally, on the bottom right over here, feedback processes are also included in the simulation. And it turns out that even upon considering all of these different processes into the simulation, the star formation rate that we get out is still a factor of 4 to 5 higher than what's suggested from observations. But it might be the case that this is not a physics problem, but instead it's a parameter space issue. And what I mean by that is that there is strong evidence that at least initially, the magnetic energy in these clouds is higher than the gravitational energy. But again, if this is indeed the case, we run into a second problem. And this is that if the magnetic energy in the cloud is higher than the gravitational energy, these clouds can never collapse under ideal MHD conditions. So if the magnetic flux is conserved and the strength of the magnetic field is, let's call it, high enough, these clouds will never collapse. And this is what I'm showing here. So this shows the number density in the cloud from a simulation as a function of time. And you can see that even after 120 mega years, the cloud is not collapsing, but is instead oscillating around the equilibrium state. All right, so what do observations have to say about all of this? Well, what I'm showing over here is the strength of the magnetic field as measured from Zeeman observations as a function of Corning density. And this red line is a theoretical line that marks 2 different regimes, let's put it like that. And here all of the different points are different clouds. So all of the points that are in this side of the line are clouds for which their magnetic energy is higher than the gravitational energy. So these clouds can never collapse under ideal MHD conditions. And then finally, these clouds over here are clouds for which their magnetic energy is less than their gravitational energy. So these clouds can go on and collapse and form stars and planets and what else. Now, in actuality, the way we quantify the dynamical importance of the magnetic field is through this parameter nu, which is the mass to magnetic flux ratio, which basically tells us how much mass is enclosed in magnetic flux tube. And if this mass to flux ratio in a cloud is higher than a critical value, then the cloud is called supercritical, and it's in this region over here. Vice versa, if the value of the mass to flux ratio is below critical value, then the cloud is supercritical, and it's in that side of the line. So in actuality, this red theoretical line marks the critical mass to flux ratio. Now this plot over here, these observations reveal a very interesting thing, right? Which is that clouds start their life being subcritical, and then somehow they become supercritical and collapse and form stars. So in other words, we need a process that turns subcritical clouds into supercritical ones. And this process is ambipolar diffusion. So what is this ambipolar diffusion? Well, ambipolar diffusion is simply a term that we use to describe the relative drift velocity between ions and neutrals in a partially ionized plasma. So in this GIF over here, the normal driving people are the ions that feel the Lorentz force and move towards the center of gravity only as fast as the magnetic field allows. And then the neutrals are the fast and the furious, which are trying to drift through the ions to get towards the center of gravity. Now you can imagine that the lighter the traffic is, in other words, the fewer the ions, the faster those furious neutrals are going to drift towards the center of gravity. Vice versa, when traffic is really heavy, all of the species, the neutrals and the ions, will move with the same velocity because of collisions. And when all of the species move with the same velocity, magnetic flux is conserved. When this drift velocity is non-zero, we can redistribute the magnetic flux relative to the mass, and we can have a subcritical cloud become supercritical.
The problem with that analogy is that if you have the collisions, the traffic will just stop.
Yes. Okay, so how does this actually look in practice? Well, what I'm showing over here are the results from a 2D axisymmetric simulation. The background image shows the density in the cloud. These blue vectors over here show the velocity of the neutrals, and then these green vectors over here show the drift velocity between neutrals and ions. And as you can see, most of the non-ideal MHD effects and most of ambipolar diffusion takes place close to the central parts of the cloud. So the neutrals move towards the center of gravity slightly faster, increasing the mass-to-flux ratio in the central magnetic flux tubes in the cloud. So this can become supercritical and they can collapse. While at the same time, the outskirts of the cloud over here, where the drift velocity is close to zero, can still remain magnetically supported. But it turns out that there is a second way through which this ambipolar diffusion controls molecular clouds. So it does not only control the interplay between gravity and magnetic fields, but it also controls turbulence dissipation. And that is because it leads to the dissipation of small amplitude perturbations in a very, very short time scale, compared, of course, to the overall lifetime of molecular clouds. So to make this a bit clearer, what I'm showing over here are two simulations with completely identical initial conditions. One was performed under ideal MHD conditions. The other one also included non-ideal MHD. And immediately you can see I hope you can see the color bar not very helpful. You can see that there is that ambipolar diffusion and non-ideal MHD has a drastic effect in the overall structure of the cloud and in the distribution of the H2 number density. Okay, so let's update our physical picture one last time. In this team over here, we should add all of the ions, because these are the ones that feel the Lorentz force. Over here, we should include all of the neutrals, because these are the species that want to move towards the center of gravity. And we should consider all of the different chemical interactions between all of these species, as well as how these ions slow down the neutrals in order to compute what is the effect of ambipolar diffusion. Now, normally I don't like to show a lot of equations in my talks, but because in these sort of simulations, the devil is usually the details, I would like to spend a minute or two just to talk to you about how I've modeled all of these processes. Okay, so we start with the induction equation, and what this equation tells us is that we can advect the magnetic field with the velocity of the neutrons over here, each time leaving behind some flux because of these resistivities eta in the cloud. And here J perpendicular and J parallel are the components of the current perpendicular and parallel to the magnetic field. These resistivities are defined in terms of the conductivities of the cloud, which are in turn defined by these equations over here. So omega is the gyro frequency of each charge species. This tau is the mean collisional time between each charge species with the neutrals. And then this sigma S is the individual conductivities of each species. So this conductivity of each species in turn depends on the number density of each species. To calculate that, I have also included a non-equilibrium chemical network in my simulations, solving 1,650 chemical reactions for every grid point and for every time step of the simulation, with a different continuity equation for each of the chemical species. In turn, this mean collisional time depends on this mean collisional rate, sigma W. This mean collisional rate, depends on the mass of each species and the drift velocity itself. The drift velocity over here depends on the resistivities of the cloud. So, yeah. After we solve this whole system of equations iteratively until we achieve 1% accuracy, congratulations us, we have found the resistivities for one grid point in the simulation. Now we can move on to the next grid point and then to the next time step. But not so fast, because it turns out that we also need to reduce the time step by taking into account the maximum resistivity over the entire cloud. And for the physical resolution that I have in my simulations, the time step turns out to be of the order of 20 years. So, yes?
What's the typical Hall parameter what's the typical Hall parameter in the cloud conditions you're simulating?
For the range of densities that I simulate is a factor of 3 orders of magnitude less than the perpendicular resistivity. But it varies by a lot from the low density parts to the high density parts by many orders of magnitude. Okay, so to recap, what we need to do is to simulate a system, a physical system that evolves over millions of years with a time step of the order of 20 years, while doing all of this for every grid point and for every time step. And this is how you end up with a simulation that took 4 million CPU hours and 2.5 years to run. But hopefully I have convinced you that there are no devils in this particular simulation. Okay, so after this very long introduction, these are the results from this simulation. What I'm showing again over here in the background image is the density in the cloud. These cyan lines show the magnetic field. These orange-yellow vectors show the velocity of the neutrals. And then these purple vectors show the drift velocity. Now, 3 things here. First of all, obviously, in the outskirts of the cloud, over here and over there, the drift velocity is very close to 0. So the outskirts of the cloud remain very close to the ideal MHD regime, so to flux freezing. Secondly, all of these vectors are perpendicular to the magnetic field. And that, of course, makes sense, right? Because in the direction parallel to the field, both the neutrals and the ions will feel the same forces. So their only separation in velocity should occur in the direction perpendicular to the field. And then finally, all of these vectors of the drift velocity point towards the center of the cloud. So again, that means that the mass-to-flux ratio we were talking earlier should increase towards the center of the cloud. So compared to the 2D axisymmetric simulation that I showed in the beginning, there actually seems to be nothing new, even though this was a 3D simulation, and even though I have included turbulent initial conditions. But it turns out that as the cloud evolves and collapses further, the situation becomes way, way more complicated. So here, these vectors of the drift velocity can point in all sorts of directions, not necessarily toward the center of the cloud. And interestingly enough, there also seems to be an anti-correlation above and below the cloud's midplane. So here, for instance, the vectors of the drift velocity point in that direction, whereas below the midplane, they point in that direction. So to make this a bit more evident, what I've done is that I took two cuts like so over here and plotted the component of the drift velocity, and this is what I'm showing over here. So with this dashed dotted line, I'm showing the profile of the drift velocity above the midplane, and with the dotted line, I'm showing the profile of the drift velocity below the midplane. And you can see that above the midplane is negative, close to the center of the cloud, whereas the other way around, below the midplane of the cloud.
These V drifts are slightly subsonic.
Sorry?
The V drifts are slightly subsonic.
The V drifts are slightly subsonic. So the reason why we included this relation between the mean collision rate and the drift velocity is that the drift velocity can become slightly supersonic. And then some approximations break down, but the way I've modeled all of these processes are to take into account a scenario where the drift velocities become slightly supersonic.
Is there a physical mechanism that maintains the sonic speed as an upper limit or rough upper limit for the drift velocities? Some instability that happens if you exceed that value?
So you mean if I exceed the
Could
sound
they
speed?
become highly supersonic?
Could it be highly? I think yes, in some shock regions potentially, not in molecular clouds or that much, but in some regions yes.
J-shocks or something
Yeah,
like that.
yeah. Okay, so what's causing this antiphase above and below the midplane? Well, to answer that question, first we can massage the equations a bit for the drift velocity, and we can bring it in this form. And what this equation tells us is that actually we can decompose the drift velocity into two components. One component associated with the magnetic tension force per unit volume, and the other component associated with the magnetic pressure force per unit volume. So over here, I'm showing the component of the drift velocity associated with the tension force, and over here, I'm showing the component of the drift velocity associated with the pressure force. So again, two things over here to note. The first one is that the component of the drift velocity associated with the pressure force is quite lower than the one associated with the tension force. And secondly, most of this anti-correlation above and below the midplane primarily occurs because of the magnetic tension force per unit volume. So what's our physical picture here? Well, I think this is best summarized in this simple cartoon. So early in the evolution of the cloud, the magnetic field lines have a morphology consistent with this configuration. The tension force points towards the center over here, and that means that the components of the drift velocity point towards the center of the cloud. At later times, however, and because of the initial solenoidal motions because of turbulence, I get these loops. So here, of course, again, the tension force should point towards the middle of this loop, but that means that above the midplane of the cloud, the drift velocity should point away from the screen, whereas below the midplane of the cloud, the drift velocity should point inside the screen. Okay, and then we can further quantify this behavior using this plot. So what this plot shows is the orientation of the different vectors of the drift velocity. So theta equals 0 here means that the vectors of the drift velocity point towards the center of the cloud, and theta 180 means that the vectors of the drift velocity point away from the center of the cloud. So you can see that again initially, most of the vectors of the drift velocity point towards the center of the cloud. This is shown with this black line over here. Whereas at later times, and as the cloud has evolved further, we get a very significant fraction of the components of the drift velocity pointing away from the center of the cloud. And we also get the second peak close to 90 degrees. So the reason why this is a very important result will become apparent in a second. But first, I would like to answer another question, which is whether we can observe this drift velocity to begin with. So you would expect again that, if this drift velocity and ambipolar diffusion is so important for the evolution of the cloud, controlling turbulence, controlling the interplay between magnetic fields and gravity, we should have observed it, right? But it turns out there are a number of challenges that makes it very hard for us to observe this drift velocity. Firstly, in order to get any sort of information regarding the velocity field inside the cloud, we need to have some spectra from a neutral or an ion, right? But then again, we will have radiative transfer effects that will come into play, which can create a distorted view of reality. Then we also have observational limitations. And what I mean by that is the typical velocity resolution of most spectroscopic surveys is of the order of 0.15 kilometers per second, give or take, whereas the typical velocity, the typical drift velocity found in simulations is a factor of 3 lower, although in the 3D simulations it was quite high. And then finally, we also have chemical effects. So to better understand chemical effects, let's imagine that we have a very simple spherical cloud comprised out of just 2 onion cells over here, which are collapsing at different velocities. And then because of some chemical effect, we have one species, in this case the neutral, only existing in the outer shell of the cloud, and the other species, in this case the ion, only existing in the inner shell of the cloud. Then any difference found in the spectra between these two species can be simply attributed to the fact that they are probing different regions within the cloud, collapsing at different velocities, and that will have nothing to do with ambipolar diffusion whatsoever. Okay, so to study all of this process simultaneously, let's go back to our simpler 2D axisymmetric simulations. And what I have done is that I have post-processed these simulations with my line radiative transfer code called IREC to create synthetic position velocity data cubes such that I have a spectrum in every location in the cloud. And this is exactly what I'm showing here. So over here I'm showing a synthetic PPV cube from the 1 to 0 transition for HCN. And on the right, I'm showing synthetic observations for HCO+. So once I have these synthetic observations, then I can go ahead and I can measure the full width of half maxima for every spectrum in the cloud. And this is exactly what I'm showing here. So with this green line, I'm showing the spectrum from HCO+. With the red line, I'm showing the spectrum from HCN. And I have also marked the full width of half maxima in this case with these dashed lines. And then in the middle panel over here, I'm showing a map of the full width of half maxima for HCN. And on the right, I'm showing a map of the full width of half maxima for HCO+. So finally, subtracting this map from this map, I arrive in this map over here, which shows the observationally derived map of the drift velocity based on the synthetic observations. But then if we are to compare this mock observed map of the drift velocity with the theoretical map of the drift velocity directly from the simulations, you can see, again, hopefully you can see that there are significant differences. But as it turns out, all of these differences can be attributed to chemical effects and the fact that HCN and HCO+ do not probe the same regions within the cloud. So now the question becomes, if this pair of species is not suitable for observations of ambipolar diffusion, is there a pair of species that we can use to probe this drift velocity? And to answer that, I went through tens and tens of pairs inside my chemical network, tried to identify suitable species. And then what I'm showing over here in this plot is normalized ratios between various pairs of neutrals and ions. So over here I'm showing CO over HCO+, this is ammonia over H+, This is HCN over HCO plus. And then finally here on the bottom right, I'm showing HCN over HCNH plus. So as you can see, this pair over here, and hopefully you cannot see this time, is the pair of species that exhibits the least amount of variation within the core. That means that these two species are co-spatial. Whereas for every other pair of species that I've tried, the variation was at least an order of magnitude. So what this means is that, at least based on these results, on these simulations, this pair of species is the best and the most promising candidate for future observations of ambipolar diffusion. And luckily enough, it turns out that this pair was also co-spatial in all of the different models that I've run, where I've changed the temperature according to the ionization rate, the visual extinction, and so on and so forth. Okay, so now I would like to go back to the 3D simulations and this part.
To understand
Why they are
why
co-spatial?
those are spatial and the others are not.
Because of the chemical network. So, for example, HCNH plus is directly created from reactions of HCN with H3 plus, and then HCN is fed back again from HCNH plus. So they always remain in sort of an equilibrium. Whereas in general, these chemical networks tend to have a very chaotic behavior.
So they're tightly coupled chemically.
Yes, that is the reason, essentially. Okay, so going back to these 3D simulations and this plot, I want to say a few words on why this is important, right? So we said in the beginning that the mass-to-flux ratio should increase in the same direction as the drift velocity. But just the fact that we have these many vectors of the drift velocity pointing away from the center of the cloud actually compels us to pose a very provocative question, which is, could we have a supercritical fragment that becomes subcritical because of this complicated structure of the drift velocity? In other words, do we cross this threshold over here only in that direction, or could we also cross it in that direction as well? Well, to answer that, first we need to measure the mass-to-flux ratio. Now, again, you could imagine that this being a simulation and me having access to all of the quantities in the simulations, that would be really trivial. It really isn't. But in a nutshell, what I do is first I take a slice through the simulation box, perpendicular to the mean direction of the magnetic field. And then for every pixel in the slide, I track the magnetic field lines through the simulation box. Then for every location along this field line, I create these small convex shapes, measuring their volume, and then measuring this infinitesimal mass elements DMI over here. And then finally, I'm also measuring the flux of the magnetic field through these octagonal surfaces. Then I add up all of these mass elements over there, and I have a way to properly measure the mass-to-flux ratio. Okay, so finally, this is the mass-to-flux ratio as a function of time. And as you can see, the mass-to-flux ratio increases as a function of time, with only very tentative indications, I would say, of that this increase might reach a plateau or even slightly decrease at very late times. But then this again depends on the area that I use, that area that I define, to sort of measure a mean, an average mass-to-flux ratio. So here, for the red points, I have used a smaller area than these black points. And then finally, what I'm showing over here is a radially average profile of the mass-to-flux ratio as a function of distance from the center of the cloud. So with these blue points, I'm showing the true mass-to-flux ratio. And again, you can see that the true mass-to-flux ratio increases towards the center of the cloud, despite of all the complications created by turbulence, and despite of all this complex structure of drift velocity. Okay, and then with these purple points over here, I'm showing the mass-to-flux ratio that we would see in observations under the absolutely best case scenario ever realized. And you can see that the observed mass-to-flux ratio does not correspond very well to the true mass-to-flux ratio. And this is simply because in observations we cannot perform a line integral along magnetic field lines. So we could be assigning the wrong mass to the wrong flux.
So how is this observational estimate made?
So I look the cloud along the mean direction of the magnetic field, and this is what I mean by best case scenario, right? And then for every location, I compute the column density in sort of a pencil grid. And then I measure again the line of sight component of the magnetic field. And I can't remember whether here I have weighted the line of sight component of the magnetic field by the relevant species that we would observe we would use to observe the magnetic field in observations. Okay, so best case scenario, we observe along the mean direction of the magnetic field. But it turns out the situation is even worse when we observe in every other direction. So this is a very busy plot, so allow me to take some time to explain it. What I'm showing over here are different lines of the mass-to-flux ratio, so 0.1, 1, and 10. And then these two blue lines over here mark the initial value of the mass-to-flux ratio in simulation, and the final the maximum value of the mass-to-flux ratio in simulation, of the true mass-to-flux ratio in simulation. And then to produce these different points, what I have done is that I have randomly selected a snapshot of the cloud at a random time, observed the cloud at a random inclination, randomly select a beam size, put it randomly in a location of the cloud, compute the column density and the line of sight of the magnetic field, and this is how these points are created. And you can see that only when we observe the cloud along the mean direction of the magnetic field, so these are the red and green points, we get out something reasonable. Whereas when we observe the cloud such that the component of the mid component of the magnetic field is perpendicular to the line of sight, we can underestimate the true mass-to-flux ratio by more than an order of magnitude. And this, of course, means that most of our observational estimates should be considered lower limits. Okay, so as I was putting together this presentation, I thought of wrapping up things here, but I actually didn't want to end up to end on a negative note. So I would like to spend another couple of minutes discussing on things that we can do. So the beauty of actually simulating the chemistry together with the dynamics of the cloud is at the end of the day, this is exactly what we observe, right? We observe the chemistry of the cloud. We observe some emission from some molecular species. And then we can also create these very beautiful synthetic observations of the same cloud, observing different molecules and in different inclination angles. So I thought to myself, why not train a neural network to actually match these synthetic observations back to the physical and chemical conditions of the cloud. And this is what I'm showing over here. On the left, I'm showing a chemodynamical simulation. I have post-processed that chemodynamical simulation to create this set of synthetic spectra for 4 different molecules, 2 different transitions per molecule. And then I have trained a neural network to match these sets of synthetic spectra back into the physical and chemical conditions of the simulation. And then over here on the right, what I'm showing are H2 number density profiles along the line of sight. So with the black lines, I'm showing the true H2 number density profile along the line of sight. And with these red lines, I'm showing the results from the validation sample of the neural network. So of course, if this holds up, that will open the way for a full 3D reconstruction of molecular clouds based on nothing but spectra.
How does it do this?
Beats me, honestly, it's like magic. Okay, so quickly summarize my take-home messages. Hopefully I have convinced you that non-ideal MHD is really important, controlling the dissipation of turbulence, and the interplay between the magnetic field and gravity. Turbulence can significantly affect the structure of the drift velocity. We can use this pair of species to observe the drift velocity. Despite of all the complications from turbulence, the true mass-to-flux ratio monotonically increases with time and towards the center of the cloud. And then finally, the observed mass-to-flux ratio tends to underestimate the truth. So thank you very much for your attention, and I'm happy to take more questions.
Okay, thanks, Aris. Very good talk, and you left us plenty of time for questions. Let's open up. During the talk.
Yeah, just want to follow up on my question. In this very dynamic situation, you can imagine that non-linearities with Hall effect are going to become very challenging to simulate. And is it clear that they get washed out largely by the ambipolar drift?
The Hall effect?
So, for example, in neutron star context, all drift in the solid crust of neutron stars is being investigated in some detail. It's a very challenging problem, the extreme nonlinearity of the equations. So I was wondering, when you consider the full dynamic range of the molecular cloud, is the Hall nonlinearities, are they really generally subdominant?
Not always. Not always. It depends on the density rates. It also depends on another other factors such as the grain size distribution that you can assume. Yes, but for this range of densities up to up to 10 to the 6, I think pretty much all of the simulations that I have personally seen show that the Hall effect is generally subdominant compared to the ambipolar diffusion.
And I mean, to what extent have these numerical approaches been tested? But I mean, you have well-defined, I think, test problems along, say, the ambipolar damping of a hydrodynamic wave. Problems like that. I mean, to what extent have you made, sharp tests of the numerics with problems like that?
For my code, you mean, or in general as a computer?
Well, I guess one should ask more generally about the community doing
in
this.
general, as a community, there have been a lot of tests. Now, if you talk particularly where I have tested the damping in a very well-defined and well-set-up scenario. Totally truthfully, I haven't. I have tried, obviously, to match previous results from previous non-ideal emerging simulations, and then I get very good agreement. But then again, I don't think that there is any other simulations that would consider all of the different species individually having different collisional rates, and so it's a matter of how many advancements you make as well, right?
My question is about distinguishing between the turbulence reconnection and ambipolar diffusion. How can this entangle the effect of turbulence reconnection with ambipolar diffusion? Because affecting almost the same to removing magnetic flux.
That is, So the problem with me answering that question is that I would need to criticize the model of turbulent connection. And I think that a lot of the effects there are numerical, they're not really physical. And I don't know if this model actually has a very well-defined prediction, whereas this ambipolar diffusion scenario has many predictions regarding the mass-to-flux ratio, how it should change, and so on and so forth. So if there is no
You can certainly
well-defined.
compare an pure MHD simulation where all of the magnetic dissipation is numerical reconnection with the one that includes the diffusion.
To compare the two and see differences, for sure, yeah.
I want to generally, theoretically, ambipolar diffusion is proportional to the drift velocity. And I didn't understand how to take care of ambipolar diffusion, because when the drift velocity becomes large, the effect of ambipolar diffusion is larger. So in your simulation, ambipolar diffusion is dynamically changed. I mean that or just considering a constant ambipolar diffusion effect.
No, it's dynamically changed for every location in the cloud, for every time step it changes constantly.
And do you know if this problem that is interestingly has some important issue, maybe it's interesting to check in other part of the, I mean that in the larger scale structure of the clouds, it's worth to study in the other media, like protoplanetary telescope.
Oh yes, definitely. The problem there is that obviously for me to use the same amount of code to do protoplanetary disks, there are some complications, meaning that I will need to sort of adjust my chemistry such that it is appropriate for protoplanetary disks. Perhaps I should also include dust growth, which I don't have over here. I just have an MRN distribution of grains. So, but yeah, I mean, definitely the code itself with these sort of adjustments could be used to model other systems as well. That's not, yeah.
So I just have a really basic question. If you just took your initial setup,
yeah,
and did the usual analytic approximation to what the collapse time would be due to ambipolar diffusion,
yes,
would you get a different answer than you're getting from Eric?
It's for the 2D simulations where I have done that, it's super close.
It's close.
Yes, within, if my memory serves me right, less than 0.5 megayears in a span of 12 megayears. So the error is
And it's roughly the same in the 3D, or is it very different?
So in the 3D, this particular simulation that I have presented here was super critical to begin with.
Okay.
But I'm running subcritical ones, so we'll see what the results do.
Can I ask about the initial conditions? I was thinking that one of the things from the beginning is the idea that the dominant effect increasing the mass-to-flux ratio is ambipolar diffusion, when there's also, of course, the possibility of just accumulating matter along field lines, from some larger context. So the initial conditions must be set up in such a way that isn't the dominant process. You already have this core, it's a well-defined object, it's going to evolve, through these, there's turbulence, but then there are these sort of quasi-equilibrium, I don't know, if ambipolar diffusion you've got in your simulations, really quasi-equilibrium, but there's a well-defined initial concentration which evolves.
No. So my initial conditions, I start with uniform density, uniform magnetic field along the z direction, and then with an initial turbulent power spectrum. And then I let
this is just what we're looking at is kind of like the place within the simulation that this. Yeah, keep going. Sorry.
And then the cloud actually relaxes along magnetic field lines together with the effect of turbulence and so on.
So it is including the flux that you're talking about. So that'll increase the mass-to-flux ratio.
No, that doesn't increase the mass-to-flux ratio because in an ideal MHD simulation that would do the exact same thing.
Right.
But the total mass along the flux along the flux tube
In
remains
vertically.
constant. Yeah. And I have actually done that test for the ID element simulations. I also have ID element V1s in order to compare with. And there you find that the mass-to-flux ratio remains constant over time, even though the, let's call it, overall evolution of the cloud is sort of similar. Still relaxes along magnetic field lines, creating sort of a flat structure.
So it's got a mean column mass-to-flux ratio.
Yeah.
The implicit in that is the boundary conditions. There's a limit of integration to integrate along field lines for when you define mass-to-flux. Like you stop at some location.
Yeah.
And say that's the edge of my box. I've counted up all the mass. You could imagine a broader situation where you keep integrating.
Or you just inject mass.
Yeah.
Well, all I'm saying is that the definition of mass depends on the boundary. And so then the definition of mass-to-flux depends on the boundary, which raises this issue of like, what's the, how do you map, how do you,
mass-to-flux
yeah,
ratio?
what's the mapping between the simulation and which some unbounded cloud in the sky?
Well, you can always argue with timescales, I would say. Like if you have to integrate throughout the entire galaxy to get a supercritical mass-to-flux ratio, then there is no way you will bring all of that gas towards your molecular cloud in a time scale that makes sense, and it's shorter than the lifetime of the molecular cloud.
So maybe there's another dimensionless parameter one could make up that includes sort of the matter that is dynamically connected to the region. I don't know, which is kind of like what you're doing, but I feel as though maybe there's some version of it which is got that point.
Well, there are other ways to quantify through length scales, for instance, to quantify the interplay between the magnetic field and gravity, between magnetic, so the dissipation again of turbulence. You can also quantify these things in terms of length scales as well.
Take a G's like take
Yeah, this is the equivalent of the G's length, the magnetic length scale, and I'm forgetting the other one, the alveolar length scale, yes.
Okay, very good. I think we'll continue some of these discussions over refreshments upstairs, so let's give Aris a hand.
circulate information location?
No, not yet. No, it's to the side.
I mean,
It'll be in the
He wants to know. So there's too many.
Right, exactly. We might end up here. Okay,
Yeah.
my real question, let me go to the real quick. I want you to hold all the questions. Because I can't hold questions.
Oh, right.
Because I'm up for renewal.
Oh, I got you. Sure.
So
I
that's.
just have
even
to,
if-
just to double check that this goes well, I do have it on my calendar. If you want to send me a reminder.
I will send you a personal reminder. Yeah. Good stuff, yeah, and yeah, we can discuss some of that connection.
Are you around tomorrow?
Yes, I am.
Are you available tomorrow at around 11?
Anytime.
We have a 11 a.m. sort of star formation discussion. Great if you could come by.
Yeah,
It's, you'll
should be an
make
80, I can forward.
So that means that it's in the other building in the basement. Do you know where the basement room is, right?
I'll find it.
Yeah.
I mean, the basement's not that big, so. I have to run, but I mean, it's.
Yeah.
Look forward to chatting tomorrow.